review and then do some brief stuff. And then I'll tell you about the last week of class. So first thing I'm going to do, did I start recording? Yes, didn't I? Yes. And I'm sharing the screen?
Not yet.
I am not sharing the screen. There we go. Hey, hold on a sec. Hey. Oh, I made it. I made it. Listen, I'm in the middle of class, so, but I just thought I'd answer you. Give me a call back later, okay? Like after 5 or something. Okay, Marty, bye. That was my brother. Just wanted to make sure there was nothing big going on. All right, so, Norwegian cyclone model. All right, and what I'm going to do is I'm going to use images to do that. So the first image all these are pretty much the same. So there's really nothing that exciting about it. But I will use, I don't know, I'll use this one. Because what I like about this one is it starts out like this. So keep in mind that the upper level winds in the jet stream are going to be like this. They're going to be parallel to the surface front, because that's what it usually is when it's barotropic. Notice that the wind is flowing parallel to the isobars. The front is parallel to the isobars, which means that the isotherms, which are going to be on the cold side, are all going to be like this, right? Everything's kind of paralleling. Now, the reality is this where the jet stream is? Well, probably not. Probably the jet stream is going to be here. It's going to be a little bit north of the boundary because there's a slant. So look at this flow in sort of three-dimensional space. And we're saying that the upper level jet is probably over here. Remember that the thermal wind is the relationship between the temperature gradient, the pressure gradient, and then the winds, right? With a couple of intermediate steps. But this is the basic idea. So the fact that the front exists says I have a strong temperature gradient. Because I have a strong temperature gradient, I have a strong, what's next? What's next after strong temperature gradient? Hi, Isaac.
A height gradient?
No, before that.
Strong pressure.
Thickness gradient.
Thickness gradient, right? So if you have a temperature gradient, that's going to lead to a thickness gradient, which causes what to happen when there's a thickness gradient?
Greater slope of an isobaric surface.
Right? The isobaric surfaces, those are going to be sloped more steeply. So that would be a thickness gradient leading to a sloped isobaric surface. But the slope of an isobaric surface is delta Z over delta X, right? Rise over run, and that's a height gradient. Then you get a pressure gradient, because a height gradient and a pressure gradient are the same thing. And then the greater the pressure gradient, the faster the winds. So in this scenario, the jet stream is moving like that. Now we already said that the front is a region of cyclonic shear, because that paddle wheel would start to spin. And what I need is the approach of a shortwave trough. So what that basically means is I'm going to get a jet stream with a little bit of a warp in the jet stream, like that. And so I know that there's going to be this area of divergence occurring somewhere downwind. And what kind of a wave is this? This is going to be an upper level trough. Because an upper level trough is synoptic scale, and synoptic scale causes the air to be the pressures to fall on the synoptic scale. So I get a cyclone developing. Once that cyclone develops, then I start to bring in temperature advection, right? I'm starting to bring in cold air and warm air advection. So when I look at this region, I'm like, okay, well, the reality is this is the area of strong warm air advection.
So are troughs always a dip down in the jet stream?
Hold on, give me a second, Sam, and I will answer that question. This is where there's going to, whoops, this is where there's going to be cold air advection. So as a result of cold advection, listen, west of the low and warm advection east of the low, then I get a region here where I get this front moves southward as a cold front. Okay, and this section of the front starts to move forward as a warm front. And the air starts to come, the cold side air goes around this way. If the cold air retreats, it's a warm front. And over here where there's warm air coming around, remember that the warm air is going to go up over the cold air. See over here, it goes up over the cold air. And the cold air comes in down, sinks behind this. Okay, so that's where we get this type of scenario. And then with the course of time, we get a more well-developed warm sector. And in the warm sector is where I get showers and thunderstorms. Now, going back to Sam's comment, what is a trough? A trough is not the dipping down.
Okay.
The trough is defined as cyclonic curvature, right? Notice it's turning cyclonically here. What's it doing over here? It's turning anticyclonically. That's a ridge. So there's your ridge, there's your trough. And the reason that becomes important is when I go into the tropics, remember, in the tropics, the surface winds are going to be northeast trade winds, and the upper level winds tend to be from the east. So the jet stream is going to look like this. And then the question is, what is this? What does that dashed line represent?
Anticyclonic.
Right? It's anticyclonic. It's curving this way, so that makes it a ridge. This is where it's cyclonic, which makes it a trough.
Okay, that makes sense, because I thought that, with the isobars making a dip down in the jet stream, like that would indicate a trough.
Right. It's not that it's a dip. It's not what it looks like. It's what it curves. Because the trough is where the air is sub-geostrophic. That's what's going on with the trough. Now, because the jet stream is basically going the opposite way, generally speaking, it's cooler to the south and warmer to the north. So in the tropics, you actually, in the upper levels, are going to get cooler air, where it might be a little bit warmer in the tropics, because the thermal wind is still going, it's reversing. So the jet stream, remember how we drew this thickness last week? We said that surfaces went like this. They're actually going to go like this. In the tropics, see it? And you see how they are sloped this way, meaning the pressure gradient force is that way. Downhill is the PGF, which would be to the North Pole, to the north. Here's the equator. But over here, which way are these things directed? Oops. Which way are these things directed?
Southward.
The pressure gradient force goes the other way, which means the jet's coming into the screen. This is the jet out of the screen. This is the jet into the screen. And the reason for that is in the summertime, especially, where is the atmosphere warmest? The atmosphere is warmest, gets the most insolation over the Tropic of Cancer, right? So if this is the TOC, Tropic of Cancer, then that's going to be warmest. So the thickness is greatest in that region. And then we reverse it slightly. So it's not much in the way of a reversal in temperatures, but it's a little bit. It's a little bit because it's warmest there, and that happens in the summertime. So we get waves that come out of the east. So keep that in mind, that depending on which way the jet stream is tilted. So if I have an upper level low, right, then this is still cyclonic. That's all troughing. Even though if I looked, imagine that I looked just at the south side of this thing, or I'm sorry, just the north side of this thing, that's still the trough. It's still an area of low pressure. Okay. So you've got this scenario now with strong cold advection. We said the coldest advection is where there's a strong thermal gradient, temperature gradient, you have a strong pressure gradient, and then the intersection is most perpendicular. So the cold front tends to move faster because it's more perpendicular, and the cold front catches up and it creates this warm sector that tends to get smaller. Eventually the cold air wraps around it, and when it wraps around it, what do we call that? When the cold air wraps around it, what do we say the air is doing?
An occlusion.
An occlusion. Cold air wrapping around it is the occlusion. Now, I want you to, this one doesn't have an occlusion. So I'm going to go close this on, and I'm going to go to this one, and notice that the occlusion is here, where cold air is wrapped around it here. I still have, what is this area in here?
The warm sector.
That's the warm sector, okay? And the warm sector has a, what we call a triple point. Triple point, because it's basically three different air masses at that point. We have the warm air mass, we have a cold air mass, and a cool air mass, or cool and cold, depending on whether it's a warm or cold type occlusion. We have three air masses, and the point of intersection is called the triple point. So technically, Sam, triple points are three air masses, not three fronts.
Right.
Okay.
That's the point to watch.
Sometimes you have this, right? You have a warm front like this. This is more for Sam and Lena, who've had some of this with severe. We have a cold front, and then what might happen is this as a dry line. So we've got basically cool air, we've got cold air, we've got warm and dry, and warm and moist. And so we have a triple point right there. We also have a triple point at the low because we have the cold, cool, and wet, warm, dry. But because it's dry air, this is not going to be unstable hugely. But you can get some good moisture. And so in Sam and Lena, you get moisture coming up this way. This is what we call the wraparound. You get some really cool stuff.
So every system like this, where the warm front meets the center and then the cold front, that's just the triple point. It doesn't have to be like, it doesn't have to be.
Doesn't have to be an occlusion.
Okay.
As long as you have three different air masses, 1, 2, 3, you have a triple point. So it doesn't have to occlude. That is a triple point also. And if you ask me, this is way better.
Yeah,
That's where I would be. near that.
yeah,
Lots of ways to do it, because the Norwegian cyclone model is just a model. It's not always the way things are. What I wanted to say here, though, at the triple point is that the jet stream, like where's the jet stream in this scenario? Well, the jet stream is going to be on the boundary near the cold and warm air. So the jet stream is actually looking like this. Notice that the surface low is starting to pull away from where the jet stream is. So over here, again, the boundary of the jet is up here. And the low is pulled into the colder air. Because remember, it's cold north of the jet, and the low is wrapped in cold air. That's the occlusion, which means the low is not with the jet. Where's the divergence going to be the most? It's going to be down here. So when we see the triple point of the occlusion, sometimes if you get another short wave, you get a new low. So you get the cyclone that develops anew in this region because an additional short wave comes.
wouldn't that be like synoptic cycling?
This is all going on in the synoptic scale. So these are synoptic cyclones. But if you look at a storm, a thunderstorm, a supercell thunderstorm, they're going to go through the same process on the mesoscale. And the tornado is where the area of low pressure is. So you would have a tornado, and then another tornado could form there, and then cycle, like you said. So interesting way of putting it, this is synoptic cycling, right? That's what it is. It's really that the mesoscale is mimicking the synoptic scale, but you get
Right.
it. Now,
Are you able to use real models to give us an example?
well, I don't know. I don't get to control the weather. I know I'd like to, but I don't. Let's see if we can find one. So I'll start with an area of low pressure. And
Dynamic tropopause.
the problem is, look at what this is. This is big area of high pressure right here. If you kind of look at the flow, it's all going around. So where is there an area of low pressure? Well, in the model, there's lower pressures out there in the mountains.
Dynamic tropopause might be able to be more clear.
Well, I know what the weather is doing, and I don't remember it doing much of anything. I guess in this scenario, this is a little bit more like traditional. So this is coming in Monday the 17th. So that's not this weekend coming up. Is it? No, it's this weekend coming up. And what I have here is an area of low pressure, and sort of a front. Remember I said you could look at this thing called the lifted index? Oh, no, that's not it. This one. And we see how the lines are kind of packed over here. So that's pretty close where the front is. So in this one, what I'm basically saying here, and again, this is not a Norwegian cyclone model. I would say that I have a cold front here. Now remember, a cold front is where cold air is advancing southward. And if I look here at this area of high pressure, I've got air coming down across the front here, 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 all over this place. The winds are southerly. So that's technically a cold front. Is there a warm front any place in here? I don't see it.
Probably in the eastern Great Lakes.
Nope. Oh, no, wait. Maybe you could say at 850, you could say here. That's the 850 front. But I don't even know if I would say that's a front here. Because remember, what are the rules for, here? I want you to go back, look at the 6 rules for finding fronts. What's rule number 1?
Look for a strong temperature gradient.
And then number 2, a strong dew point
Dew
gradient.
point gradient.
So I see a temperature gradient going from the 60s here to the low 50s there-ish. Maybe during the day. I guess I get a little one over there, but at this point, I would say I don't see one. I don't see a temperature gradient over in this area. If I said dew point temperature, I see a little bit more of a temperature gradient. So, you know, you could make some argument that, well, there's sort of a front here someplace. That's what I would say. But why do I have to find that? The reason I find things like that is because I said, well, gosh, this is what the Norwegian cyclone model predicts. But in this case, I have an area of low pressure, 2 areas of low pressure on a cold front. So this is how I would analyze it on this, if this was a real day. I would say that's what it is. It's an Arctic front. Now, where will the jet stream be? Let's take a look at the jet stream at this time frame. And the jet stream has kind of got, there's sort of a flow here, and there's sort of another one here. See, it's not exactly what you would expect. So rather than that, maybe I could go to 500 millibars and look at wind speeds, and it's like, this isn't what you talked about, Paul. Here's a stronger jet, but over here it's not much. And that's because it's just sort of there. I look at something called vorticity, and I see areas of strong color indicate the shortwave. So there's a shortwave there. There's probably a shortwave here. But it really, this pattern doesn't really look like the Norwegian cyclone model. Because in reality, weather is way more complex. When the Norwegians came up with this, they had a few stations that came up with these concepts, but in reality, you wouldn't probably come up with the cyclone model. So now what was the book? What did the book talk about? What was their model? The T-bone model? That's a T-bone. Synoptic cyclone. There we go. This looks a lot different, doesn't it? And that's not really probably a good one to discuss. I guess the official name is the Shapiro-Keyser cyclone. So you kind of have a front, and then it sort of makes this T-bone shape with an occlusion. It's still occluded. You know, you can go into details and just give examples of these things. So it's a little bit harder. So one of the things that they've done, and I'm going to show you this. Would be a conveyor belt weather systems. Hold on a sec, guys. Hello, Jennifer. Okay. Oh, yeah. Sure, I can do that as soon as I can. I'll take a break with my class. And what time's the board meeting? It's Wednesday or Thursday? Thursday. Okay, I will be there then. Okay, terrific. Thanks, Jennifer. All right, bye. Okay, sorry guys. So they have this new thing called conveyor belt system. So let me show you this. Now, in this one, you have the area of low pressure, which is still there, and you got the warm front and the cold front, just like we've seen it. But notice that the warm air goes up, goes over the frontal boundary. So whenever there's warm air advection, what that means is air is rising. But the air that rises goes up and it turns to the east. That's the warm conveyor belt. So you can see these arrows here indicating that. Now, when we've got the dry conveyor belt, this is really usually it's with cold air, but the air comes down and then sinks behind the cold front. So it's going to be that continental polar air that's going to sink behind this area of low pressure. There's a weird thing here, and that's the cold conveyor belt, which usually comes in north of the warm front and it wraps around in the upper levels. It's way more advanced than I want to deal with you, but I just wanted to show you how complex the weather systems really are. So sometimes this cold conveyor belt has a little bit more moisture, and that moisture can then come up there and create the comma head clouds. So that comma head cloud is all in here. And actually the moisture goes one of two ways. It goes this way or this way. This is called a call point. So if you're ever interested in real, more advanced synoptic meteorology, you need to go into some of these detailed concepts of things. And there's a lot of cool pictures. So this is almost like the T-bone and the models. And they give you some examples. A lot of times they do stuff in England and Europe because it's more obvious than in the United States. Do you know what makes them difficult in the United States? Like even over here, what makes it difficult here is that we get a lot of problems with this area here. So you have the Rocky Mountains here. And the fact that this is whole mountainous area really messes things up. So you don't see these cyclones till off to the east. So, Sam, you asked me, could you show me an actual one? I don't really see a good one traveling across very well. Although, well,
it might be.
actually, you know what? Let me look at this one. This one is kind of interesting. So this is the Atlantic. I'm going to show you what's going on with this area of low pressure right here. Okay, there's an area of low pressure. Colors indicate temperature, so it's really warm air here. A little bit warm air out here. It's covered, it's cooler because of clouds. But watch where that low goes, okay? That low moves across, and look at how much deeper it gets.
Northeast.
Do you see how the isobars wrap around it? And what's happening here is the cold air is starting to wrap. The warm air is confined here. And so what we really have is an occlusion that's taking place right there. And we said in about 24 hours after the occlusion is when it's the lowest pressure. So watch as we go a little bit forward into time. It gets really low there. Like Sam said, it's like a nor'easter. Aaron, remember we were talking about nor'easters? But watch what happens after this.
Wow, look at that one.
It gets really spread out. This one gets there's a new one that gets really big out here. Man, this is so.
You're gonna get rogue waves with that one. Up
So
there.
over here at this point, the low is kind of stuck out here. It becomes a closed upper level low. It just kind of hangs out there like a rock in a river. We have an area of low pressure here and a very strong area of low pressure here. This is occluded. This one has a warm front, pretty well defined with the winds, and a cold front over here. So do you see how the low is formed with the second one, that there's an occlusion? And then this guy gets really big. That's really strong. That's a really big storm heading into parts of England. So it's just fun when you look out in the Atlantic. A lot of times you see these really big systems. They're not as fun for us. Notice our temperature on May 21st, 76. Possible. It's going to be nice. We're in the middle of high pressure this weekend. It should be nice. Let's see what we got. According to this, we have rainfall possible Sunday night. Our temperatures, what do we call this up and downness of the temperatures? What's that called? Isaac, remember what that is? Are you guys there? I
Yeah,
don't hear any.
Aaron says diurnal.
Okay, that's the diurnal cycle. So do you see that there's a pretty strong diurnal cycle? Temperatures get down pretty cold though, based on this. And the weird thing about it is that the average high is like 69 going to 70. So we're pretty far below normal. And our average low is like here. So we're 10 to 15 degrees below normal. And then when we don't see the diurnal variation of temperatures here, what's the reason for that? What do you think's going on here?
Overcast.
Right? So we get clouds, maybe overcast, precip. So I'm hoping we get better weather. I'm supposed to go someplace nice this weekend. in Illinois, in Ottawa. We'll see. The models have been really inconsistent, but sunny days for these 3 days, then cloudy, then sunny again next week. Okay, so that's talking about weather. Now I want to show you something. Let's go to the Pancus Hank YouTube channel. We are in this one. He's got educational storm videos. Let's go here and see them all. Here, let's look at this video.
You know you've written a successful poem when people really think it happens.
They're different. Okay, so but to make it easier, what I'm going to do is I'm going to take this. It's only 5 minutes, so we'll meet back here in 5 minutes, or you can stay on. But I want you to individually watch this. Just mute yourself. You watch it this way. You can take notes on this a little bit, okay? And I will share that link for you in the chat room. Okay, there's the link. So go ahead and watch that, and I will be back in 5 minutes. Okay. Let's get into your notes, some basic stuff. What are the 3 types of thunderstorms?
Single cell, super cell, multi-cell.
Man, you have the worst audio. You know that, Nina?
Does this help? Does it help if I turn off my camera?
Yeah, a little bit. It does make it better.
Okay, thanks. Yeah, my Wi-Fi's gotten so bad.
Well, you need to do something about your Wi-Fi. Maybe somebody's stealing it. Okay, so get out your book. Actually, I like the book. I love this section on cyclones in your book. I think it's really good. By the way, turn to page 187. Those are your Norwegians. They're pretty cool. Carl Gustav Rossby founded the Chicago School of Meteorology. University of Chicago used to be a really big name meteorology, one of the best in the country. Who was the famous scientist, meteorologist from the University of Chicago you know? You've all heard of him. Ryan?
Not sure.
Sam?
Fujita?
Fujita, Ted Fujita, have you heard of him? Am I sharing my screen?
No.
Never heard of him. Don't know who you're talking about.
Where are you guys? We're going to come to this in a second. Well, actually, no, I can do it this way. So Ted Fujita.
He actually came up with the microburst theory.
Yep. So Dr. Ted Fujita came here after World War II, but that's where we get the enhanced Fujita scale, which measures the intensity of tornadoes. So that goes from EF0 to EF5. So he came up with that scale called the Fujita scale, which measures how strong, how much damage really. It measures the intensity by how much damage it does. Okay, so you probably should know that. Anyway, he was the University of Chicago. So Rossby is one of the big ones. We talked about Rossby waves. He was just really big. Anyway, turn the page. We get to thunderstorms. We've already kind of talked a little bit about ordinary thunderstorms. So on page 190, we have done that before. And then we talk about what are the conditions, what are the things that we need for thunderstorms. We need lift, moisture, instability. I think we've mentioned that before. And then what determines the type is the amount of vertical wind shear. If we have very little, we get single cell or air mass thunderstorms. So if I'm not sure if the book necessarily has this about those, but Pecos talked about that at the beginning, single cell storms. When we have a moderate amount of wind shear, then storms start to organize and we get multi-cell storms. And then with a lot, we get what we call supercells. And the supercells are what Pecos was talking about. A supercell is the rarest and most dangerous type of thunderstorm because the updraft has what?
Rotation.
It has rotation. That rotation is called a mesocyclone. So this is what Sam and I were talking about before, is that a supercell storm is a mesoscale low pressure system, mesocyclone, as opposed to the synoptic scale cyclone. And the Coriolis force is not as important in a mesocyclone, and there's a lot of things to learn about it. If you want to learn about supercells, you need to make sure that you take severe and unusual weather, Earth 1115. That course is really intense. But take a look at page 196. And we have an area of low pressure where the tornado is, but you see how there's sort of fronts associated with it? Those fronts are called gust fronts. Gust fronts. So instead of a warm front, you have the forward flank gust front. Instead of a cold front, you have the rear flank gust front. And the rain evaporates, causes cooling air, and you get the occlusion. We said the tornadoes are determined by the wind scale or the wind damage surveys. It's called the Fujita scale. It says Tetsuya, which is his Japanese name, but he went by Ted Fujita. And then there's just some stuff in there that you've already read about. So we're not going to go too much into it, but look at page 198. That diagram sort of is a picture of an area of low pressure, cold front, warm front, and this thing called a dry line. But this is just such brief coverage of thunderstorms. We're not going to go into it. I'm not going to expect you to do much. I have an entire class devoted to this. So if you want to know about it, that's the class to take. Okay, any questions on the thunderstorm part? I do want to show you this one video though, and we'll watch this one together, okay? So this is a 17-minute one. It's a little bit geeky. So here's the deal. I want to see you watching. You do not have to take notes on this, just enjoy.
Hank, it's great to see you too. It's been a while.
So there's Pecos Hank.
Since our last discussion, there's been a lot of progress with your work and with your team. High on that list is that you've grown another superstorm in a supercomputer that drops a long track EF5 in an environment similar to a historic environment that also did the same thing. That's correct. So about a year ago, you and I had a little conversation on your channel where we talked about my simulation of the 24 May 2011 storm in El Reno, Oklahoma. Now, one of my research goals and the research goals of my team is to not just do this for one storm, but to do this for multiple storms. So for the last year or so, we've been searching around for different environmental conditions to initialize our model with so we can grow some new storms. Dr. Catherine Finley at the University of North Dakota took a sounding. This is the National Weather Service balloon launch data. So anybody can go online right now, go to the 18Z Jackson, Mississippi sounding from 27 April 2011, download that sounding and run it in a cloud model, and it should produce a tornado if you run it at high enough resolution. So we're pretty excited about this. The storm that we have produces a long track EF5 tornado on the virtual ground for at least a half an hour. April 27th, 2011 was the big outbreak.
Look at that.
There was a F4 tornado in Tuscaloosa, Alabama. There were multiple F4s and F5 tornadoes in this event. From my perspective, what makes the Southeast so challenging is the topography. You as a chaser, of course, would agree, I think. It's a difficult region to study because of all the hills and all the trees.
Yeah, you usually get a one shot of those storms. You know, it comes, it flies by you, you get your 5 minutes if you're lucky a video, and then you try to catch up to it, but then you have to stop because there's trees in your road, there's cars in your road, there's people in your road.
So we sought out.
Pretty cool, huh? Did you, Sam, were you saying something? Oh, okay.
That event, because it was such a major event,
Your team has finally had some time to analyze the data.
Yeah.
Or you've had more time.
more time.
You're developing some pretty solid theories on tornado genesis and making some pretty bold statements.
Yes, I continue to make the assertion that you do not need a rear flank downdraft to have a tornado, or at least to maintain a strong tornado. So one of the leading theories of tornado genesis involves a downdraft in the rear flank that triggers a tornado. And you addressed that really well in our first talk. And so far as I know, that theory does not extend to the maintenance phase of the tornado. What our theory does not contain is a trigger. We do not have a triggering mechanism that leads to the tornado. What our simulations are showing, and what's sort of becoming clear, is that the updrafts can be very strong, very close to the ground. And this is something I think that is a relatively new discovery. The amount of stretching that the updraft can do is a lot more than we thought, because the updraft is stronger than we thought near the ground. It's almost as if, when you look at what's going on near the ground, that the storm itself is finding ways to consolidate vorticity. It doesn't matter if it's from the environment or if it's from the cold pour the storm has generated itself. But it's basically taking all this horizontal vorticity from different areas, it's converging it towards the center, and then it's abruptly tilting it into the vertical. When that horizontal vorticity is tilted into the vertical, it then becomes vertical vorticity, which contributes towards the mesocyclone and maybe even towards the tornado's rotation, because that rotation has to come from somewhere. What we've discovered is, in the vicinity of the SVC, the air pressure is dropping like a rock. When you have very low pressure just above your head, it's going to create a pressure gradient that is going to make the air want to go up, okay? If you create a vacuum, air will go into fillers. It's like one of the fundamental forces of nature. That's the pressure gradient force. So what I'm thinking is going on is the SVC results in a lowering of the pressure. A lowering of the pressure results in a strengthening and a lowering of the updraft base. The strengthening and the lowering of the updraft base results in extreme stretching and tilting of vorticity near the ground, which ultimately results in a tornado.
Okay, so let's stop just for a second. So I know there's a lot of little weird stuff in here, and I don't want you to get overwhelmed too much, but He's talking about stretching and vorticity or spinning. That's really what it is. So this is like the ice skater, the figure skater who spins, and then she pulls her arms in and spins faster. What is that concept called? Do you know what that concept that you spin faster if you have a smaller radius?
Angular velocity.
It's dealing with this angular what? There's another word. It's the conservation of angular what?
Momentum.
Momentum. Okay, so that's what that's called. So what they're saying is when you have something spinning like this, if you can stretch it, it's going to narrow it, it's going to make it smaller, and will spin faster. So that's what they're saying the tornado is. A tornado in its very essence is just rotating air, and then it rotates really fast. So I do want you to write down this into your notes someplace. The definition of a tornado. A tornado is a violently rotating column of air. A violently rotating column of air in contact with the ground and the cloud. And that's what's defining this thing to be a tornado. Okay? And so the question is, how do you make it rotate so fast? Air likes to rotate. Part of it is that it squeezes. You stretch this vortex. So violently rotating column of air in contact with the ground and the cloud. That's what a tornado is.
Not only does it result in a tornado, but it helps to maintain the tornado that forms. And again, this theory is not in stone. I would suggest that what explains the clear slot and the big wraparound that occurs prior to tornadogenesis, instead of it being a cause of tornado, I think it's an effect of the rapidly lowering pressure in the lower part of the mesocyclone. The air is responding to that drop in pressure such that air that would normally sort of scoop towards the rear and just continue to go ends up getting pulled back inwards, so it gets sucked around this big low pressure region. So perhaps what you're seeing is the pressure drops, then you see the wraparound in the RFD, then a tornado forms. I'm not going to claim to solve this problem. I don't want to appear like I have. I just have an alternate theory, at least, for the specific type of storm that we're studying.
Okay, so Sam and Lena, because you've taken this, we talk about the rear flank downdraft, the occlusion being so important, and it is, but only in the sense that the occlusion is happening, you can visually see that, and that's when the tornado happens. The question is, well, why does that happen? And he's saying, well, the pressure is what's dropping first. That, whatever, right? That doesn't matter. That's from a perspective of looking at it, doesn't matter. They're together.
Downdraft in the rear flank to trigger or to even maintain the storm. I'm arguing that it really has to do with the forward flank, the SVC, and other things.
You know, I'll also throw out that I've been underneath storms with big tornadoes on the ground, and there appeared to be no RFD on the back side of this thing. And oddly enough, there's no RFD. This is really weird.
See, and that's more like what ours is. It's funny, one of the students who's looking at this work, along with my collaborator, Catherine Finley, she said, where's the RFD? It's like an RFU. See, that would be consistent with our type of tornadogenesis regime. You essentially have a parade of vortices coming along the forward flank of the storm. At some point in the storm's evolution, when that pressure drop becomes really intense, everybody just goes towards that location. Convergence just happens and everything just gets concentrated into one spot.
Going further back in time, it's the pressure drop.
It's the pressure drop. And then the question is, what leads to the pressure drop? And that's why I'm honing in on the SVC, because the SVC is definitely a region of low pressure. So if we can find out what causes the SVC, when do SVCs form, when do they not form, then maybe we can say, well, an SVC is formed in the storm. That might be an indicator that it's going to produce a longer tornado than normal or something. We don't know yet. Okay, but
for those of us in the chasing thing, Sam, I call that the big suck. When a tornado, you know that things are going, and you're just like, oh, something's going on.
When the inflow just starts ramping up.
Hypothesizing why we're focusing on these features is because they might have diagnostic predictability qualities where we can use them to maybe give people a better idea of the kind of storm that's forming. And again, that's really my ultimate goal. If the SVC is real, we find in nature, then the question is, okay, how do we detect them and how do we use them as a new tool in our toolkit for forecasting to give a better prediction of what that storm's going to do? Can we? I know that some people think the SVC is just along for the ride. Maybe something else is leading to it and it's just getting sucked up and it's just a passive thing. I don't think that's true, but it's up to me to prove that or to show that, and that's what we're working on. So someone like me can only publish my results if I do my due diligence on observational work as well. It's very rare that you'll publish a paper that just talks about the model simulation and doesn't look at the real atmosphere, because what's the point?
With that, what do you say we go look at some of the matches? And I wanted to see what you thought about some of the matches that I have picked out for us.
Sure. All right, let's do this.
Let's open up comparison number 1.
Yes.
So this one is one of my favorites. I think if you don't know anything about supercells, you might see all those lines and stratification, and you might think like that doesn't look natural.
Right.
But a storm chaser will say, oh yeah, that's kind of the ideal storm you want to see. You want to see an updraft that has all that wind scope, and we just go crazy for that. One of the things that I really like about this comparison I've done is you've got these extensions, these appendages at 2 different layers streaming in from the south into the updraft, and your storm rendered something very similar.
This is why I love this collaboration we have, Nick, is that I'm just gobsmacked by how similar these 2 images look. In the Tuscaloosa storm, the storm we're calling the Tuscaloosa storm, the new one, you get these cloud bands, and when I animate the storm, you see that sometimes they come and they go.
And look at even the wall cloud.
Yes.
There's even a
Little tiny little tail.
yeah.
No, well, let's go on to the next one.
Okay, so the next one, this was the same atmosphere after that storm died. Another storm popped up to the north. And again, I'm using this just to say, look, here's another storm with all of those wind sculpted striations to show people that, yeah, this is actually common. And we do see that weird looking UFO shaped updraft.
This is really amazing what you've done here. I wanted people to understand this. I mean, you're coming up with stuff that looks really similar. And again, I can even count the layers in the layer cake. You got 3 of them. And I just have to say, tremendous work. So this says to me that the model that we're using is probably doing a pretty decent job when you can actually create something that looks a lot like Mother Nature. In the simulated storm, you have a very clear tail cloud. You see a similar feature in Hank's image there. And you see striations in the barrel-like mesocyclone. And you can certainly tell that there's rain falling in the forward flank. So very nice comparison.
Awesome. Thank you. Let's move on to number 3.
All right, number 3. Oh boy, it's all about that tail cloud, isn't it?
Yeah, so on your other storm, we had all different kinds of tail clouds. We had the long streaming tail cloud, and on this one, you just kind of have a nub.
You have a nub, exactly, but that happens all the time.
It happens all the time, and here's a storm that I got this year in Colorado. I was like, wow, this tail cloud is very similar to the one that I witnessed. So I just want to show that this little nubby wall cloud is actually a very common feature that we see in these storms.
Exactly, and another thing I would say is, look at the rain foot in my image, the black thing.
Yeah, oh wow, I didn't even notice that. Right, how it's bending into the updraft, right.
You can sort of point your way to the updraft by the way that rain foot is oriented.
That's over here.
Yeah. You see
Rain's coming down.
So there's another similarity between those 2. So excellent.
Awesome, sweet.
Okay, I just want to say that I've never seen this. This is great. This is great stuff.
I've watched all of his videos.
Pecos Hank is just a great guy. He's a really superhuman being.
You get the chance to meet him, do it.
And number 4.
Number 4. Oh yeah. Oh God.
There you go. So this is one of my favorite storms. This was the first tornado of the day. And again, you got kind of a little tail cloud. You got these tiers in the updraft of the mesocyclone, that little vaultish area. And then perspective, the tornado relative is pretty similar spatially.
Man, I gotta tell you, that is just so cool. As a modeler, when I see stuff like this, I just go, wow, because I spend a lot of time looking at the stuff
If
on the
you-
right, which is like, okay, it looks good.
You got to admit, though, right? I mean, I've never seen this. This is what the storms look like. And this is what the numerical model, he basically this. So Zach, when I talked to you about doing, maybe you should give up games and go into meteorology. This is the kind of stuff as a programmer you can do is you can actually take programs, models, numerics, equations, and generate images by doing things like this and putting them together. It's just phenomenal stuff.
But it's a model. But when I see the stuff you got, it warms my heart because it means that we're on the right track. And as a scientist, you might think I'm crazy to be so conservative about my opinion, but I'm very, very aware of how it's easy to have your own sort of a confirmation bias where you're seeing things and you're focusing on the thing that you think is there already. That happens in
So
science.
what you gotta do, doing it for you, it's always comforting, right?
It helps. That just means it just says, look, chances are we're getting this stuff right because Mother Nature is Mother Nature. She's doing what she's doing. The model is essentially the laws of physics as well as we understand them. So this means that when I start to present results, really quantitative results from our work, and I show images like this, it's going to be hard to argue against my theory should at least be plausible because look at Mother Nature and look at the simulation. They're very similar. So one of the things about our simulation is that the tornado condensation funnel doesn't always extend to the ground, and that has to do with the issue with the way we handle the microphysics. In a real tornado, if you get rain in the tornado, it gets spun outwards, it gets centrifuged outwards. Our model doesn't have that physics in it yet, so sometimes our tornado gets filled with rain, and that ends up sort of eating away some of the clouds. So sometimes you don't see the condensation funnel all the way to the ground, but rest assured there is a tornado on the ground. And a tornado itself can be on the ground causing damage, and there not be a condensation funnel. That is certainly occurs in nature as well.
Oh, yeah, I can show you plenty of video of that. If there wasn't any dust, you wouldn't even know there was a tornado there.
Exactly. So that happens in our model sometimes, and sometimes it happens for the right reasons. Sometimes it happens because, oh, well, we got to find a way to get that rain to spiral out of the tornado. Again, it's work in progress. And that's true of anything scientific. When you see somebody, a scientist talking about their work, rest assured that they're not done. It's always work in progress. It's always just keeping the needle pushed towards the direction of understanding and understanding what's going on in the world. But that's a beautiful comparison right there.
Yeah, this is kind of a new storm for you. Your last storm, by the time I caught wind of it, you had been lecturing about this storm for 2-3 years, and I had a plethora of angles, and there was no problem getting all these different results. Really, all that I've gotten from you so far is this one rendering, and with that one rendering, I was still able to get a lot of close similarities. So again, in my opinion, that's a supercell.
That's a supercell. I'm of the same opinion, eh? And as we've talked recently, using some new software, I can change the angle and move the box around and such. And we can do more of these comparisons. And at some point, I wouldn't mind just getting you in front of the software where you can actually start playing with the stuff too.
I would love to do that, and an opportunity might present itself as I'm traveling through. And then afterwards, we'll go storm chasing again. So I did send you some requests because I have this one shot where I'm following a storm in Canton, Texas, and the mesocyclone is cranking, and it's got some different tiers in it. I felt like, man, this might be a good match, but I don't know if it's really the same structure of the supercell. But I'd still like to see it, and I'll put them side by side for any of our other viewers to see what I was thinking, how they differ. I think it'd be cool to see how they differ.
Yeah.
One thing that I want to point out to a lot of people, there's several different kinds of supercells that can drop strong tornadoes. I mean, there's things called mini supercells, which might not drop EF4 or EF5. I bet there has been one somewhere down the road, but can still drop powerful EF2, EF3 tornadoes. And then also you have the classic, like you got, of that El Reno beast, massive updrafts. And you can also have supercells that are really skinny. They almost look like tornadoes just dropping out of a cumulus tower. And those are just glorious to observe.
That's Hannibal.
This particular one that I'm talking about dropping long track EF4. So even that type of supercell looks really different. I imagine over the years of doing more and more simulations, you're going to get all these different kinds of supercells that look really different. And that will probably help you zero in on some of the similarities that are causing these long track tornadoes.
Absolutely. Yeah, we're going to be doing more storms in more environments, not just the long track EF5s. We're gonna be looking at the tops of the clouds, not just the bottoms. You know, we'll see what happens. We'll just toss it in the pot and make some gumbo and see what comes out.
You know, if you could get a cyclic supercell,
Yep.
and I'm talking about a subset of a subset of a subset, but something like Pilger, and I mean, that's really.
Look at that storm with two
crazy,
tornadoes.
Unique scenario. We've got two long track,
That's Pilger.
but having two on the ground might double the chances of seeing some of the features and the currents. How awesome would that be?
That would be so awesome, dude. I have tried to simulate Pilger. We got a sounding that looks like a loaded gun sounding, looks great. And we ran the model and basically it just dies after like half an hour. The storm goes up and it just, oh. So clearly we have more work to do to understand Pilger. Now, Pilger was especially, as you say, it was a subset of a subset of a subset. You had two cyclonic tornadoes. That is weird. That type of storm, and let's also mention 31 May 2013, the big 2.6 mile wide. Those are
Fringe cases.
fringe cases. But sometimes the fringe cases will tell us things that we wouldn't even know to ask about. I have simulated May 31st, but it doesn't produce a 2.6 mile wide EF4, EF5 tornado. But I'm still working on that storm. As you can imagine, these things are complex. You know, the modeling world is far from ideal. And we have far from ideal initial conditions to feed the model in most cases. So the fact that we're able to get something that looks reasonable is really a testament itself. Science can be a whole lot of fun, Hank. We don't know what we're going to discover. That's what makes it so much fun. As we continue to do these simulations, we're going to have different tornadoes, different situations, and we're just going to unwrap this stuff and see where it takes us.
All right, well, keep us posted on all your new developments, and thank you again for sitting in with us.
Absolutely, Hank. Take care, and thanks for having me on.
Okay, so I hope that was kind of interesting to you. Severe thunderstorm, I think this is a couple things I want you to know. Severe storm definition. I think we've already talked about this. Let's go to this. What's the difference between a watch and a warning? First of all, what makes a storm severe? I think we've already said this, haven't we? Hail, 1 inch in diameter. 2 would be winds greater than or equal to 58 miles an hour, which is 50 knots, if you want to know. And then 3 is a tornado. Right? I think you've had that. And then what's a warning? Well, a warning means that conditions are producing a tornado. Okay, so a warning means it is happening. And there is imminent, and I want you to know this word, imminent danger. It's usually short, means when do you act? When you have a warning, when do you act? You act now. A watch means conditions are favorable. Means look out. Be on the lookout. So I'm going to show you another little video here. See some new things that the National Weather Service is doing. No, that's not what I want. Let's go to the videos. Uh, yeah, I went to high school with, I mean, college with this guy. Has some warnings. Well, maybe this will work.
Good afternoon, and thanks for joining today. My name is Eli Jack, and I'm an alerting protocol.
No, this is not what I
apply
want.
to consolidation and reform.
Has some. Let's go to their page. Maybe we can find this. I'm going to this tomorrow. Project overview. Now, I guess there was a nice little video they gave a while back, and I don't know if they've taken that away. It seems to be point. I'm sorry, guys. I thought this would be easier to find. Maybe they got rid of the video on the internet, because I certainly don't see it anyplace. I want a video. Oh, well, I'm not going to get a video. Well, just to give you some idea of hazards, because I want you to see this, let's go over here to this hazards page. And this is basically what's going on. So what we've done here is we've colored anything that's dealing with fire weather to be orange. So we have a red flag warning that basically means there's extreme fire danger, parts of Northern California. Anything in purple is winter. So look at this. We have frost advisories tonight, freeze warnings up to the north. I mean, this is May 11th, and we're setting record temperatures. So we have a frost advisory. If you click on that, it says portions of Northwest Indiana, West Central, East Central, North Central, Northeast Illinois. Frost could kill sensitive outdoor vegetation. Temperatures 32 to 35. That's crazy. If we go back to this one, we can go to blue would be marine warnings. So there's gale warnings is the type of wind if you were a boater. Yellow is tropical. Green is hydrological. So there's flash flood watches and a lot of flooding in the south. I don't know if you've seen that on the news. Non-preset might be dust or wind. Here's a high wind watch. And then non-meteorological. So over here might be air quality alerts. So this whole map gives you that kind of stuff of what's happening in the weather. Special weather statements going on over there. No, nothing big that we need to worry about. So those are the hazards that we address. And severe weather ones are going to be some of the bigger ones. So here's our Storm Prediction Center. And there's a chance for hail and winds and thunderstorms, even maybe a tornado or two along the Gulf of Mexico. Just been really cold. I'm going to look at one more thing here before I move on to the next topic. Local storm report, record report. April 27th, a record high temperature at O'Hare, 87 degrees. Rockford, record high temperature. Some rainfall amounts. But as I said, the climate statement for DuPage showed you a record. What's the record for tonight? 36. If it drops down to 35, 3 days in a row, that will set a record. And that, I find that kind of interesting, don't you? Oh, I guess it didn't get down. It didn't set a record the day before. No, it set a record today because it was at midnight. Hold on. I'm going to look at something. Here's the for DuPage. At DuPage, it got down to 33 last night. So that's a record. 35 the night before, 33 last night, might be low 30s again. 3 nights in a row in the 30s in May. That's brutal. Anyway, so that's some severe weather. Let's go to here. Take out your notes because I want to make sure you're all set. Academics, class notes, intro, unit 4. There, you can read that, make sure you understand that. And then the last thing we want to do is talk about a little bit about hurricanes. Okay, so turn in your book to page, what is that? 201. And actually 202. So there's a diagram. It shows you where all the action is. So I can do something like this. Global hurricanes. And we might see this picture here. So the question is, why do we not get hurricanes over here? We get a little bit. What matters the most? Why is this area not getting hurricanes? And most of the hurricanes and tropical cyclones are to the north. What's the answer? Hello? I'm waiting for you guys, students. Talk to me, somebody.
Could it be that there's not much instability in that area?
Take a look over here. What are the things we need for hurricane of development of tropical storms? The key is this first one, where we have to have warm SSTs. What does SST stand for? Sam?
Sea surface temperatures.
Sea surface temperature. We need to be, it says 26 here, probably more like 27 degrees Celsius for a hurricane. By the way, we start out with as a tropical disturbance. One, and then it goes to a depression. Basically, a tropical disturbance are thunderstorms in the tropics. If you see thunderstorms in the tropics, that's a tropical disturbance. A tropical depression is when it's a circulation. Number 3, it becomes a tropical storm with wind speeds greater than 35 knots. And then what does it eventually become? It becomes a hurricane when the winds are greater than 64 knots. Sorry. Okay, 64 knots, and then we start getting a tropical storm. That's around 74 miles an hour. Okay, by the way, on page 202, 2, you see that they're all the same storms. Hurricanes is a Western hemisphere. If you go into Asia, they become typhoons or tropical cyclones. But they're all the same thing. Okay. Page 203, they have categories. Those categories are called the Saffir-Simpson. Scale. So you see 64 knots makes it a category 1. I guess this is 34 knots. It doesn't matter. It becomes what it is when they name it. By the way, this is when they give it a name. Okay, and the key thing here is the sea surface temperatures. Okay, so what I'm going to show you here is I can show you a map of sea surface temperature. And notice how much colder it is here. It's a little bit warmer here, but you don't really get much. And the reason is, if you look at a better map, there's not much room between Africa and South America, and you don't get the wave disturbances. So most of the stuff's to the north. This water here off California is very cold. Where it's really warm is down here south by Mexico. And so anything that develops here is called the East Pack storms. Which is Eastern Pacific. So when you look at page 202, you can see the tracks close to Mexico. When they come up here toward the United States, it gets too cold. And so very infrequently will you ever get anything like a tropical storm hitting the coast. Maybe a tropical depression on occasion, but very infrequently. Lots in the Atlantic, obviously over here in this warmest part of the ocean, because if you look here, this is the warmest water. That's where you get these big tropical cyclone hurricanes, typhoons. Funny thing is, when you look at this page, we need the Coriolis force, right? Because they're rotating just like a system. They're long lasting. The Coriolis force matters. These are synoptic scale. But the third one is interesting. Remember, we want vertical shear. The more vertical shear, the more significant the thunderstorm. But we don't want vertical shear when we get to hurricanes. And that's going to be really important that you know that. So if the winds are from the northeast or the east at the surface, we want northeasterly winds aloft. And that's what we did earlier today when we said we have waves in the upper atmosphere. And over here is where the air is divergent, because that's downwind of a shortwave trough. This is what we did at the beginning of class. Okay. If you go to page 205, they give you a little bit of the structure of hurricanes, and they've got the eye. And here's a little talk about the eye of the storm. We've got bands. Sometimes we think of a hurricane as being a band of storms coming into it, like this. And here's the eye wall. And so this becomes, oops, this is the symbol for hurricane. Spiral rain bands, and then around the eye, this is the eye wall. Big storms in the eye wall, that's really bad stuff. And then the eye is, and then there's just information about this. We can get a lot of thunderstorms in the spiral rain bands, We can get tornadoes in those spiral bands. Not many tornadoes here, not much lightning here, but in the spiral bands, certainly more than that. So again, you can take a
Usually
look
the northeast quadrant bands.
if it's moving that way, or the right front quadrant. Page 205, you see some pictures. Now, page 206, I want you to take a look at something. What are those blue lines on figure 12.5a?
So isobaric surfaces.
Those are, thank you, good. Those are the isobaric surfaces. Notice in the middle of a hurricane, those isobaric surfaces are further apart because you have what's known as a warm core. So if I can find a picture online like this so we can look at it. Warm core, low weather, maybe that'll work. Is a warm core low looks like this. Bad colors. By the way, I saw something, Isaac, your colors were weird. Your fronts were weird on the diagram you put in there. I don't know where you got it from. I'm glad that you put it in there. It's just kind of weird. So the surface area of low pressure, which means the air is converging, spiraling in, then the air rises. But because there's so much latent heat, creates the warm core. The vertical distance between isobaric surfaces is greater in the middle. And what that leads to is the development of high pressure aloft. See, it reverses and the air is diverging. So we have air converging and then diverging. And it diverges anticyclonically. So if you look at page 206, figure B up on the top, see the arrows coming in into the low and then diverging and anticyclonically spiraling from the high. And that's all because of the thickness relationship of the warm core generated by a lot of thunderstorms. Obviously, there's a lot of winds, which means the isobars are really close. They talk about tropical waves, tropical storms, blah, blah, blah. We just kind of go into that. Then how do we kill it? We have more friction. Is what eventually kills it, or cold water. So when we go here, take away this. If we have cold water kills a hurricane. A lot of shear kills a hurricane, or at least weakens it. Temperatures relatively constant over a large area. Well, where do we find temperatures changing rapidly? Near a front. So when I look at a front that's associated with an extratropical cyclone, and that's baroclinic. Fronts are baroclinic zones. We do not want this for hurricanes. That's why we want temperatures constant over a large area. And then we need something that generates thunderstorms. We need a tropical disturbance, an area of thunderstorms. Most of them come from Africa. So if you want to kind of read through this a little bit, gives you an idea. The last thing that's super important that I want to talk about hurricanes is where they do damage. Obviously, they can produce tornadoes, although that doesn't do that much damage, doesn't kill many people. You can have wind, high wind, and that's pretty hazardous. It destroys a lot of things. But the biggest thing is water. Inland, it's flooding. Oops. Flooding rains. Near the coast, it's called storm surge. Okay. And the storm surge is look what it says here, most deadly and destructive part of a hurricane. The water sloshes in. So what I want to do is this. And we'll look at video. Let's go to this one from the Weather Channel.
Storm surge is often the deadliest part of a hurricane. Let me show you what that looks like, starting with a 1 to 3 foot water rise above normally dry ground. Now, this might not sound like much, but remember, this is storm water being pushed by the wind. We know that 1 to 3 foot of storm surge can knock you off your feet, stall out cars, and even carry cars away. It is too late to evacuate when the water rises to this level. But let's go above that. Let's go 3 to 6 feet, for example. Very large objects can be carried in this kind of flowing water. They can act as battering rams and enhance the damage. Let's go even above that. 9 feet of storm surge. This kind of storm surge is not survivable unless you move to the higher floors of whatever section you have to be in. So please follow the advice of local officials and evacuate as ordered when a hurricane moves in.
I want one of those platforms because those platforms show up all the time. You know what? I got to show you this one too. This is a great one for winter.
Check out this blizzard. I am up in the clouds, way up as a matter of fact. About 6,500 feet. It's a long way down there. Snow's flying all over the place, and oh, wait for it. Yes! Oh, there's snow, baby. I always get myself in these situations. We'll say that for a second. All right, listen. This is a monster winter storm, but there's a wrinkle in the forecast. Let's take this down a little closer to the ground. I'll show you what. All right, there's so much warm air feeding into this piece that these falling snowflakes are actually melting. In fact, most of the precipitation around me is rain, which is not good because down near the ground and all the way around you've got temperatures holding at 29 degrees. The cold air is so dense, it remains locked in place. The warm air has to go up and over that cold air. The rain doesn't have time to refreeze and sleep else. So now we have to deal with accumulating ice. Just 1/10 of an inch makes roads and sidewalks extremely slippery. 1/4 of an inch can break branches and cause spotty power outages. And once you're over 1/2 inch, serious problems ensue. Ice storms can cause billions of dollars in damage. They can hit ground transportation, aviation, and power sectors really hard. I mean, just look at these power lines. All right, those ice signals must be, oh, gee, you gotta be kidding me. Where did that come from? That giant ice signal just fell from the cell tower. These ice missiles, they reach speeds of 90 miles an hour and land 1,000 pounds of force. Just look around. Ice collects on everything. Look at the stress on these power lines. Hundreds of pounds of excess weight cause them to sag, and sometimes you can snap the poles that they're attached to. And you know what? The same goes for the trees. Ice can increase the weight of the branches by 30 times. You hear that? Here it comes. Oh! Holy smoke! Whoa, enough. There goes the power. Power's out. Thank goodness nobody was sitting in that bench. You know what? Look around. There's nobody out here. Nobody on the roads. Businesses are shut down. Schools closed. That's exactly the way it should be when you have an ice storm of this magnitude. What the heck is that? You gotta be kidding me. The bus? I obviously spoke too soon. This is not good. Look, the bus is already starting to slide. Look at that. 150,000 plus accidents per year. It doesn't matter if you're in any bus or four-wheel drive. You're going to slide on the ice. 40,000 people get injured. You know what? I hope this bus stops. 500 people lose their lives. That's 500 too many. You know what? It's a good thing that there are no passengers on this bus. You don't ever want to be on the road in these conditions. You're putting yourself and others at risk. Stay at home and be ready to deal with extended time without power because the crews are not going to be able to get started until the ice storm stops. I've had enough of this. Stay safe. I'm out here.
I do have to say, the Weather Channel and these dish things, I really like it. I think they're fun to have. So I just thought I would do that one. The last video I want to show you came Katrina storm surge video. This was some guys in a hotel in Gulfport, Mississippi. And there's a big 13-minute video if you want to see more details about it, but I'll just show you the shortened version. That's 2:36.
Highway 90. These walls are going to start coming bumper's coming off. Well, we're in the lobby here of our hotel. We're completely underwater.
So this is coming up in a matter of an hour.
Chairs close by.
There's no one in the car. It's just the water's hitting the brake.
Big leg. Watch the door. There's the door. See the water gets sucked out. Well, the only shot I can get is out our fourth floor. We're 4 stories up. You can see the water, the surge is dramatically risen.
Amazing wind, huh? So pretty crazy video of what that looks like. And that's the storm surge. Okay. Let's see. Where are we? Okay. Any questions on any of that stuff? So what do you have due? You have your end of the unit notes and everything. So get those notes turned in. Everything should be turned in before class on Thursday. And everything else will be a 0. On Thursday, we're going to review. I need to review with you the worksheet that you guys did on the physics, because there's some, I gave you points for doing that, but you got some of those answers not necessarily correct. So I want to make sure you have that. After class on Thursday, I will make the final exam available because I have a good idea of where your grades are. Anyway, that test will not be, there will be no short answers. It's all going to be multiple choice. So it's all online. Once it's graded, then you're done. So you will have the rest of the day on Thursday, Friday, Saturday, and Sunday to take the test. Does anybody have a problem getting it done by Sunday night? Anybody need other time other than the weekend? Then there will be no class next week. Okay, since you're taking the final outside of class, we don't need to have the final during class time. So this Thursday will be the last day. That's your chance to ask any other questions. And then once it's done, the test will be there. I think the test is going to be about 120 points, something like that. But it'll all be multiple choice or short answers, stuff that you can type into the computer and get graded automatically. Okay. All right. I'm going to let you go early so you can finish up your work, and then I'll see you on Thursday.
Well, I want to talk to you after.
Okay, no problem. The rest of you guys, I will end the recording, and I'll see you guys on Thursday. Bye.
Right.
Yeah.